Hello everyone. Jim Malis here. I just want to talk to you guys a little bit. We'll figure out how we're going to do this. I'm probably do as many problems as I can. I'll try to talk to you guys as best I can as well. This is for Physics 209. We're going to try to do very many problems from there. Initially, let's start with chapters 1 and chapters 2 from Physics 209, the Katz book, first edition. Chapters 1 and 2 is where we're going to start. These are some problems I'd like to do. As such, let's actually start talking a little bit. I will eventually erase this just for the interest of having Blackboard space when we do it, but you've got this on camera, so you can always, sounds good. Thank you very much. So you've got this on camera, you guys, so we're going to be okay. You can always rewind and see exactly what I'm talking about. So let's see what we have right here. From chapter 1, number 54, what's happening? Well, we are talking about Newton's law a little bit. In chapter 1, they're saying Newton's law of universal gravitation. And let me get into the camera here, guys, a little bit. I got to read it. I got to put it down somewhere and read some stuff, but. Problem number 54 from chapter 1. Newton's law of universal gravitation, F equals G m1 m2 over r squared, gives the magnitude of the force exerted by two particles with masses m1 and m2 on each other. The SI units of force are kilograms times meters per second squared. G is the universal gravitational constant and r is the distance separating the particles. What are the SI units of G? Well, I mean, there's a number of ways you could pretty much play this. Okay, guys, I'm going to come in and out of the screen sometimes a little bit with you guys, but we got it. Let's see what we can say here. I mean, I'm not... Number of ways you can go here. I think to me, the easiest common sense way to look at it is write Newton's law of universal gravitation, actually write it down, and then play it from there. I would leave it in non-numeric symbolism like this and solve for G. Multiply by r squared on each side and divide by the product m1, m2. So you got something looking like this. And from there, you can kind of determine the units. I mean, they're saying, we know that F is if we look at the book, look at the definitions of stuff. Remember what we said now, force in general. We talk about forces. Force is mass times acceleration. There's other ways you can talk about force, and maybe this is a bit, if I'm bold enough to say it, maybe this is a bit too simplified when we say something like that. There's a more general way to look at force, and involves change in momentum over a period of time. The rate of change of momentum is a more broad definition of force. And Newton, of course, brilliant as he was certainly aware of that. This, for right now, is fine. This gives us enough right now. Force equals mass times acceleration. It's kind of the bread and butter way to look at it. So it's a real good gut feeling way of looking at it. Mass times acceleration. Force equals mass times acceleration. Well, mass is kilograms. Acceleration is meters per second per second. So force is kilograms, meters per second per second. So the force right here is kilograms, meters per second squared. R is meters, so you square it, it's meters squared. That's meters. These are kilograms, and kilogram again. So you can kind of go here. Notice you stay with the non-numeric symbolism here and get a little more explicit down the road right here. This is true at least in terms of the SI units, ignoring any kind of numerical constants or anything. So as far as just what we can say here, this is, you can put, if push comes to shove, put a 1 right here, put a 1 right there, put a 1 right there. A 1 here, a 1 here, and see what we can say, They cancel. Meters squared times meters is meters cubed. Meters cubed per second cubed over kg. So what we got here is meters cubed per second squared times kg. Put the kg in front or in back. That's not a real big deal. But these are kind of the units. You might want to, I don't whatever. That's not, I'm not looking to split hairs with anybody here, guys. But they're saying essentially this is what's going on right there when you look at that for 54. For 57, they're talking about a pretty fascinating problem. Let's see how we can actually discuss it, I guess you could say, guys. Let me... Forgive me, guys. I just want to get these erasers out of the way here. For 57, you guys, they are talking about kind of pretty fascinating situation. Here it is. For 57, they're saying, during a visit to New York City, Lil decides to estimate the height of the Empire State Building. She measures the angle theta of elevation of the spire atop the building at 20 degrees. After walking 900 feet closer to the iconic building, she finds the angle to be 25 degrees. Use Lil's data to estimate the height h of the Empire State Building. Well, a picture's a better way to kind of look at this thing than anything else, I would say. So, you see what I can say here. For this one right here, (57). Now they're saying, that it's a lot. I mean, we have to look at the way they draw it in the book. I think is the best way to kind of do something like this, guys. Otherwise, it's potentially confusing. This is the ground. Assuming it's flat, and assuming I know how to draw something flat, which I didn't, and let's draw Lil. And I guess we're not, we do this, we can estimate her height, estimate the height h of the Empire State Building. We're almost assuming, given the Empire State Building is so high, we're almost saying she has no height, So this would be a person right here, and this would be a person right here, 900 feet closer. So there's 900 feet between the two, between two positions here. So we got this and we got that. It's 900 feet. As she looks, this drawing is really going to be not the best. This is the Empire State Building. And person here. Same person. There's this right here. This is how she looks to the top of the building there. And that's her line of sight. And that's her line of sight right here to the top of the building. This angle right here is theta. This angle right here is another theta. So I guess we could, it's a whole bunch of ways we can do it. This angle, though it's not a good drawing on my part, maybe I could improve on this. Yeah, it's a little bit better. That's angle theta. That's also, this is theta 1, this is theta 2, whatever you want to say. This is the bigger of the two angles. She's looking up. The closer she gets, the more she's got to tilt her head to look up. And that angle is 25 degrees. Here, that angle is 20 degrees. So that's kind of what they're talking about there. She measures the angle theta of elevation of the spire atop the building at 20 degrees and find the angle. And then when she gets closer, she measures it at 25. So this is theta right here, and this is the angle, you know, this is theta 1, this is theta 2, or this is theta, and this is phi, whatever you want to do. We got to figure out what the language is on this whole thing. Now, we're not really worried. I mean, they never told us, you guys, they never told us how tall, you know, they never told us how tall Lil was. So we're not really regarding her height as something very significant. If we did, we could find this height right here, and then add here. Maybe the person's 5.5 feet tall. Maybe they're 6 feet tall. You know, whatever, however tall they are, and we take that way. But they're not really. I don't think they're going in that direction. They're not asking us to do that. And so I'll try to be very explicit when they're saying something like that. But let's look at it. I mean, follow this stuff pretty closely, guys, and you see it in my notes as well. All of this stuff is in our notes. All this stuff is in our notes, okay? So, see where we are. I mean, let's take a look at, you know, I'll try to follow my notes relatively closely. I mean, my drawing... I mean, if I must say, my drawing in my notes is perhaps a little bit better than it is up here. It ain't much of a difference. The big thing here is that's kind of the look. Now, I'm kind of inviting, you're really, at the end of the day, you guys, you're really caring about this, and this height right here. And this height right here is really the height of the building. Her height right here doesn't really get counted. So the way I did it in my notes is better than how I drew it here. So let me kind of, when we do that, so I'm going to go in and out of the screen a little bit sometimes, guys. And okay. So we're looking at this. Let's kind of go back to it a little bit. It was fine the way I drew it. It's realistic the way I drew it initially on the board, and you're just going to have to ignore the height of the person in question. You're assuming they got no height. So maybe an easier gut feeling way to do it is, okay, here's the ground, and well, here we go again. I don't want to. I don't want to draw the person. We're gonna assume that they're so short compared to this massive building. Here they are, and here they are again, and that's 900 feet between them. It's the same thing I draw earlier, but this is somewhat easier to look at, and you're looking at the Empire State Building, and we're, again, the different angles we're going to take on this thing. You got this one. You got this one. Nobody's going to mistake me for being an artist, that's for sure. And you got this right here. And that's maybe a little more of a gut feeling way to look at it. Once you've drawn that, this is really that's really the leg of a triangle. That's another leg of a triangle. This is a leg of a triangle. You know, this is length. The short leg is here. From here to here. From here to here is the short leg X. From here to here is the difference between two locations. So this right here would be X plus 900. So long leg is X plus 900. That's this. Short leg is just X. Going straight up this way, that's simply the height of the building. And that's the same in both circumstances. So I could be looking at, you guys, the two right triangles when I do this. And that's maybe a better way to do it. So this is definitely of interest. This is really the way to go here when we're going to do something like this. This whole thing right here comes out to that. And like I said, you got a hypotenuse here, and you got another hypotenuse here. I don't think we're going to need to deal with the hypotenuses. I think we got a better way out of this mess. So let's see what we can say on that. Okay, so I'm about to erase this part of it. So you have it on here. That's what we're taking a shot at right now, chapters 1 and 2. Let me do 57 from chapter 1, and let's go to chapter 2 afterwards. Okay, so Physics 209, so let's keep going. Okay. I'm kind of limited in space, you guys, so I gotta make sure we can get this thing done okay for everybody. Okay, so you got 57 right there. So we'll go here, still work with 57, and we'll kind of take it from there as we need to do so. So what's going on? Is there a way out of this thing? Can we figure out what we're doing here with the two angles? I think the most innovative way to go is consider that there are indeed two triangles, you guys. There is a right triangle. There's a right triangle with a 25-degree angle, a 90-degree angle, and the complement of the 25-degree angle is a 55-degree angle. So 55 degrees, 25 degrees, 25 degrees, 90 degrees. Now there's another triangle right here. Kind of contained, they're kind of overlapping each other. But as we said, 25-degree angle, 55-degree angle, 90-degree angle. Here, the big triangle, 90-degree angle, 20-degree angle, 70-degree angle. This is 65, forgive me, I'm sorry. 25-degree angle, 25-degree angle, 65-degree angle, and 90-degree angle. 20-degree angle, 70-degree angle, and 90-degree angle. Maybe there's something here. Maybe there's a way out of this thing. Well, I'll tell you what. Is it true that opposite over adjacent is tangent? Is it true that h over x plus 900, h over x plus 900 would be the tangent of 20 degrees, and h over x would be the tangent of 50 degrees? Maybe there's something there. Maybe there's enough mathematics I can pull this thing off. I could end up answering a lot of questions here that I'm not even, or at least a couple questions, a few questions that I'm not even being asked. They're asking me for the height of the building. They're asking me for the height of the building. That's fine. We'll go one step further. I could tell you how far she was initially from the base of the building. That's x plus 900. Then I can tell you how far she was after she walked 900 feet. I just subtract 900 feet from the answer, the original answer. Then I can tell you the height of the building too, which is really what they're asking. But we can probably kill a whole bunch of birds with one stone if we have to. Is it true? Is it true that the tangent of 25 degrees, and let me go back and forth with the glasses here, guys, a little bit. Is it true that the tangent of 25 degrees is h over x? Yeah, we just said it's a big triangle. It's a big triangle. It's not the biggest triangle. The biggest triangle is the one that has a leg of x plus 900. But here's a triangle. Here's x. Here's h. Tan 25 degrees is h over x. Tan of 20 degrees, it's going to be a smaller value. And if the denominator is bigger, it'll give you that smaller value. That's the key to the whole thing. That's the key to the whole thing right there. If you grind the numbers, you guys, I'll tell you what. This equals that. This equals that. If you divide this by this, it's the same as dividing that by that. Let's go ahead and do it. Okay. Yeah, looks pretty good to me. Let's see what we can say. They are saying that the rate, you've got the calculator, just be careful. Make sure when you're using the calculator, make sure that you have the right units. Make sure that if you're using radians, the calculator is set to radians. If you're using degrees, the calculator is set to degrees. Pretty obvious stuff. Make sure that's happening. Make sure that's going on. The tangent of 25 degrees. The tangent of 25 degrees is some answer. The tangent of 20 degrees is some answer. When you do the ratio, it comes out to about 1.28. The ratio of these two things is 1.28. So I'll tell you what I'm going to do. 1.28 divided by 1. That's the same as 1.28. This divided by that. A fraction divided by another fraction is the first fraction multiplied by the reciprocal of the second fraction doing the dividing. That flips over. The h's cancel out. And some of the beauty of the mathematics, you guys, you're right here. This right here is going to end up solving for x. How far is she from the Empire State Building? How far is she from the Empire State Building when she's walked closer? Okay. How far was she when she was 900 feet further back than the closer number? Well, I'm just going to add 900 feet to it. That's pretty easy. I can answer both those questions. Then I didn't get asked those questions, but I could answer them. So, let's talk. I mean, you got this right here. Let's just do some math and figure it out and see where we can go. We are going to come back to either one of these and get the answer, and we should be fine. Let's multiply by x on each side. X plus 900. That's the same as 1x plus 900. The rest, ladies and gentlemen, is algebra. The rest is algebra. Subtract 1x on each side. Divide by 0.28. You get 3,214.3 feet is how far she was when she was closer. When she was 900 feet further away, just add 900 feet. Well, nobody asked us either of these, but they could. It's a valid question. You got to be able to answer it. What they did ask us was, what's the height? And the height, is h. So you can, at that point, you can use either one of these. Let's use that one. Maybe it's easier. Let me solve for h. Let me multiply by x on each side. H equals x times the tangent of 25 degrees. H equals x times the tangent of 25 degrees. H equals the 3,214.3. The tangent of, let's see, we actually put some numbers here. The tangent of 25 is 0.4663. And the rest, you just grind out the answer. You grind that out, guys, you got what H is. H is, pretty close to 1,498.8 feet. H is 1,500. H is about 1,500 feet. Again, all these notes are going to be there for you guys. We're doing the very best we can with the taping. This is a real good situation we've got set up. Is it ideal? No, nothing's ideal. I mean, none of these circumstances are ideal. If we had more, if there was more resources, it'd be easier. The people with whom I'm working are outstanding, however, and this is really good. This works great. Obviously, the most clear way would be somebody to be filming me and walking with me, and I could use a lot more of the blackboard space. The picture would be a little better and everything, but this is great. This is still going to work great. You've got all of my notes anyway as well. That's the important thing. And you've got them there as well. And I like this, relatively live, you see me doing this. So hopefully this is helping you guys out. Okay. Still trying to judge how close I should get to the camera, you guys. Is about right for me to talk to you sometimes. All right. So that's it. That is some of what I wanted to show from chapter 1. Read these chapters as best you can, you guys, and then do the problems. Everything in physics, and mathematics, as far as I'm concerned, is problem solving. You don't know the physics, you don't know the mathematics until you can solve problems. The best way to learn how to solve problems is to solve problems and to have somebody show you how to solve the problem. So hopefully this is going to help out a little bit for you. Okay. See what else there is that we can kind of say here, guys. I got to get off. I'm off the screen a little bit sometimes and look at what I'm doing here, and I'll get back on the screen with you guys as well. The audio quality is excellent compared to some other stuff that you could potentially see. The audio quality should be pretty good for you guys on this stuff. Okay, so we're looking at this. Let's see what else we could say here. Let's go to chapter 2 and look at a few problems from there as well and see what we can say. Okay, guys. Going to chapter 2, we said the problems that were going to be that we thought were going to be of some interest for us, and let me kind of get to that. Once again, please forgive me, guys, here on this one. Let me get into the camera shot here, talk to you a little bit. For chapter 2, let's try problems 30, 56, 57, 69, 79. Let's take a look at it. Let's take a look at problem 30. Let me read that out, and we'll take it. Now, there's an awful lot that goes on, and they get into vectors a little bit. They talk about a bunch of stuff. I mean, I'm kind of a little bit debating how I want to go about this. Let me see what I can say here, guys. Let me say a couple things here before I even start with the problems. There's some pretty useful stuff that goes on when you deal with vectors. They talk about scalars and they talk about vectors in physics and in other places. But scalars and vectors, how they compare to one another. You know, a scalar is a quantity such as mass or temperature or money, you could say. There's no direction associated with it. There's just a magnitude associated with it. It's a scalar. A vector is something that has a magnitude and a direction. Okay? And that brings us into the realm of this thing called vector analysis. They analyze how vectors, how you operate with vectors, how you do math with vectors. Very useful stuff when you're doing physics because so much involves vectors. There's ways we can kind of go back and forth, and sometimes you don't, if there's a straight line motion going on, you don't need to explicitly be mentioning a vector quantity. If I know the direction that something's happening or I'm asking for a magnitude, there's ways to sometimes get around it. You can never fully get around it though. Vectors are vectors. They have a magnitude and they have direction. A magnetic field is a vector quantity. A velocity is a vector quantity because there's a direction and a magnitude associated with the motion. Acceleration is a vector quantity because there's a magnitude of there's the magnitude of the acceleration that's taking place, but there's also the direction in which it's happening. Am I putting the brakes on? Is it a negative acceleration? Yeah, the acceleration is opposite to the actual motion that's taking place. The acceleration is opposite that. So on and so forth. So acceleration, velocity, a magnetic field, force is a magnitude and a direction. So on and so forth. As we said, mass is a scalar quantity. The magnitude of something, the magnitude, if you just talked about the magnitude, that's a scalar. So there's a lot that goes on here, guys. Sort of debating where to go with this. I mean, the book's got different, kind of provides different emphasis. At some point, I think we have to make certain comments, I guess you can say. So there's a lot going on, and I guess the best way to sort of put it is in three-dimensional space, which is the world in which we live and work with, and I don't, you know, if you're talking about mathematics, there's some beautiful mathematics out there where they talk about, you know, n-dimensional space. You know, a mathematician can have as many dimensions as they wish with which to work, with which to do a calculus problem, with which to do a particular problem. I'm dealing with 10-dimensional space. There's 10 variables here. There's 10 axes. There's 10 axes or axes. Each one is orthogonal to the other, perpendicular to the other. I don't know how you do that. Short of the biggest place you can do that and look at it and say that's a 90-degree angle, it's orthogonal, is three-dimensional space. But you know, I guess for a mathematician, they can say there's n-dimensional space, and each one of the axes is orthogonal to each of the other axes, and you can do calculus problems with that and do a whole bunch of things. Okay. It's not our business right now. For right now, we're going to deal with three-dimensional space. And three-dimensional space, there's an x-axis, a y-axis, a z-axis, and there's different ways that gets written too. If you were to draw, and I'll draw this in a particular way here. I just want to kind of, there's sort of debatable how you want to do this, but okay, that's the x-axis, that's the y-axis, and this is the z-axis if I could draw three dimensions on a board, which I cannot. But here's x, here's y, here's z. And it's a right-handed coordinate system. You can deal with coordinate systems. You can construct coordinate systems in many ways, and you can play the rules in many ways. There's much that is sort of made up in the process. However, once you've agreed on the makeup of the process, you've got to follow rules to be able to solve problems. You got to be very consistent. So, I'll kind of make the long story short here. I mean, there is something that is 1 unit long going this way, something that is 1 unit long perpendicular to it going that way, and something that is 1 unit long going this way. I can tell you that the number 1, the distance from 0 to 1 on the number line, the distance from 0 to 1 on the number line is one of the most fascinating distances there is. It is the measuring stick of practically everything, if not everything, that goes on in mathematics. You construct the negative numbers. I'll draw something else here. Here's the number line, here's 0, here's 1, and that little distance right here, that distance from 0 to 1 is the measuring stick of everything that goes on in mathematics. If you go this way, you get positive numbers, positive integers. If you go this way, you got positive integers. If you go that way, you got negative integers. If you do fractional parts of this, you got fractions, you got mixed numbers, you got decimals. I can construct anything. The positive numbers go to the right, the negative numbers go to the left. If you go up the same exact distance, this is I. From 0 to I is a length of 1. It's also every bit as big as this is. If you go down here, you get to negative I. These are the complex numbers, the imaginary numbers. And this right here is a negative number, right here, negative 1. I can construct all the numbers, real, imaginary, complex. I can construct all of them from the distance from 0 to 1. The number I in the complex number system is no bigger than the number 1. The measuring stick is 1. The distance, more specifically, the distance from 0 to 1. It's a big thing. Well, you see this written in different ways. A lot of times they'll say from here to here, that distance is I hat in the x direction. This distance is j hat in the y direction, and this distance is k hat in the z direction. And how big is I hat? Well, they sometimes write it like this. They put like 2 big lines like that. Other times they just write an absolute value symbol, and it means the same thing as those 2 lines on each side. 2 lines, 2 lines. They just go 1 line, 1 line. It means the same thing. That absolute value symbol, or like this, means magnitude. How big is it? It is as big. It is as long. How big is it? How long is it, they're saying? It is as long as j hat. I hat and j hat are the same length. They're just in different directions. Well, I'm not worried about, these are vector quantities. How big are they? Well, first things first. They're all as big as the number 1. They are the distance from 0 to 1. That's how big they are. They go in different directions. They go in different, they're all going in, but they're as big as the number 1. It's as simple as that. Sometimes they write it, I've seen, you see it in different literature. The I hat, they'll write it as x hat. The j hat, they can write it as y hat. And that's maybe a little more intuitive even. And the k vector, z hat. The little hat they put on there just means it's one big. It's a unit vector, and it goes in a particular direction, and it is a vector. So they talk about stuff like this, you guys. And there's a lot that happens. There's a lot that goes on, you guys. So let me see what I can do here. Let's see some stuff we can say here. If you had 2 vectors in 3-dimensional space, let's say two vectors. Let's say a vector was, just trying to debate here how I want to actually write this stuff, you guys. A vector is a big vector. Now, what does vector mean? Vector means this thing, for example, has magnitude. Say my hand is 0, 0, 0 is the XYZ coordinate system origin. This is a vector. If I go here, it's a vector. Comes out at you, vector. Goes back this way, it's still a vector. Same size vector. Its size doesn't change, but its direction changes. These are different vectors, I guess you could say, different vector quantities, depending where it's oriented and how long it is. But if it's the same length, the direction makes it a different vector, so to speak, if I were to draw different vectors. This is in the x direction. What's the projection of this thing in the x direction? Put an I hat right here. What's the projection of that thing in the y direction? What's the projection of that thing in the z direction? In other words, if there was a vector coming out, let me just try to, let's say that was a vector. There is, if you go down here, there's an a sub x in length. If you go over here, there's an a sub y in length this way. A sub y, a sub x, and then somehow projected, if it was coming out, there's an a sub z in length. So if you had this thing out there, you could project this way, that way, this way, and you're just doing the project. How does it project onto the x-axis? Well, that's a sub x. How does it project on the y-axis? That's a sub y. How does it project on the z-axis? That's a sub z. So I'm writing it like this. If you had the same kind of argument, if you had b vector is b sub x, I vector, b sub y, j vector, b sub z, k vector. Well, here we go again. So what we have is, so we have this. We have two different vectors. You've got, now vectors don't add the way money adds. I'll make that clear. This is very important. What I said here is true. This is a vector sum. What the heck does that mean though? If AX is 50 and AY is 100, if AX is 100 and AY is 200 and AZ is 300, 100 plus 200 plus 300 is 600. Yeah, that's true, but not here. Vectors don't add like money adds. It's not like you gave me $100. Three people saw I needed some money. One person gave me $100, another person gave me $200, and another person gave me $300. 100 plus 200 plus 300, $600 is what I got. They loaded 100 kilograms onto a truck. Then they loaded 200 kilograms onto a truck. Then they loaded 100 kilograms onto a truck, then another 200 kilograms, then another 300 kilograms were loaded. 600 kilograms are on there. Yeah, they add just like that. The kilograms add just like the money. You gave me, you gave me $100, person A gave me $100, person AX gave me $100, person AY, person 1 gave me $100, person 2 gave me $200, person 3 gave me $300, $600. They add just like the scalars add just like you're adding money, just like you're adding mass. How much mass did I put on that truck that I now got to move all that mass? I got to drive it to New York. Okay? Yeah, that's how it adds. These don't add that way. Vectors add like triangles. Vectors add according to the Pythagorean theorem. The Pythagorean theorem. Much of what the ancient Greeks did in their mathematics was definitely cutting edge, forever to be remembered. Pythagorean theorem is probably not something that they had done. They probably got that from people before them. The Egyptians, Babylonians, others. Likely, I don't know where, it's not theirs. It's probably not there. other things they had done, when Archimedes had done elements of calculus and stuff, that was probably cutting edge, among the first times ever done. Much of their mathematics was definitely cutting edge. The Pythagorean theorem is not among those. They got that somewhere else. Everything adds according to the Pythagorean theorem. All vectors add according to the Pythagorean theorem. I can't say to you, give you an example. Give you an example. Let's go two-dimensional space. This is length AX. This is length A sub X. It's not multiply, that's just a subscript. These are just subscripts down here. B sub Z, A sub Z, A sub Y, B sub Y, etc. That's that. That's this. And you got this. We're going to say A. A means magnitude of A. The magnitude of a vector, or just put absolute value symbols. I'm kind of in the habit of doing this because the books I saw it had this. The magnitude of a vector is a scalar. The magnitude of a sub x I hat is just a sub x. The magnitude, because a scalar times a vector is a vector, the magnitude of a sub y j hat, the magnitude of that vector is just a sub y. If I was talking about the magnitude of a sub z k hat, that's just a sub z. Look at this, guys. If this is, I'm going to do a 3, 4, 5 triangle. It's a 90-degree angle right here, a 3, 4, 5. If this is 3 and that's 4, that's going to be 5. Why is that? Because you got this. You got c squared equals a squared plus b squared. You deal with this great theorem right here. So many things involve that theorem. You could get into electrical engineering and this theorem shows up. The Greeks were brilliant in their use of it. Predates them. Other stuff they did was definitely cutting edge. That ain't among them. That's something they borrowed. Luckily they borrowed. C squared equals a squared plus b squared. They call it the Pythagorean theorem. That Pythagorean theorem occurs in physics everywhere. Einstein used that theorem, believe it or not, in his theory of relativity. C squared equals a squared plus b squared. It got used there. This gets used in physics everywhere. It gets used in electrical engineering. You wouldn't think triangles would be coming up in electrical engineering. They do. Adding things like triangles, looking at them like triangles. C squared equals a squared plus b squared. If you square root both sides, square root both sides, you got that. Whatever, that's neither here nor there. The big thing here is, man, nobody is saying C equals A plus B. Nobody is saying C equals A plus B. C equals A plus B when I'm adding money. You gave me $3 and your friend gave me $4. They saw I was short on money. You gave me $3, your friend gave me $4. $3 and $4, I have $7. C equals A plus B in that regard. 3 plus 4 is 7. I get it. If I'm talking about a vector 3 units this way, and another vector, if I'm talking about a vector 3 units this way, and another vector 4 units that way, 3 and 4, in terms of a vector sum, is not going to be, that ain't 7. You'd never cut across a property to get somewhere faster if you added vectors like you added money. You add vectors like you're dealing with triangles. You're always doing this stuff as though you're dealing with triangles. You're resolving certain situations in that regard. What is going on here? What's going on here is, here's C, here's A, here's B, here's C, here's A, here's B. or A here, B, it doesn't matter. C, A, B. Okay, let's see what we have here. You ain't adding it like it's A equals AX plus AY. I ain't adding money. It ain't $3 and $4 is $7. Yeah, if I'm adding money, it is. It's not how it works here. It's a lot of stuff. I can solve for anything there. If I got any two of those, if I got A and AX, I can solve for AY. If I got AX and AY, I can solve for A. If I got AY and A, I can solve for AX. Or if I have AX and A, I can solve for AY. If I got any two of those, I can solve for the third one, but I got to be careful. I'm not talking about money here. I'm not talking about scalars here. I'm talking about vectors. And you add vectors, you manipulate vectors by dealing with triangles. They add in the form of the Pythagorean theorem. Even in three-dimensional space, believe it or not. The Pythagorean theorem doesn't escape us. That theorem is everywhere. Theorem is everywhere. So that's how you would do this. I understand. You gave me $3, your friend gave me $4, I have $7. Yeah, that ain't 7 right here though. This right here is 3 squared is 9, 4 squared is 16, 16 and 9 is 25. What number squared is 25? A is 5. If this is 3 and this is 4, then this is 5. It ain't 7. So this is how vectors add. A vector sum is just like, hey, let me draw all the components and then let me build a box and let me draw the diagonal of the box, and that shows me if I draw this in three-dimensional space, I got to build a box, and the far corner of the box is what a vector is going to be. Where it is, how big it is, well, how big is it? That's crazy. Believe it or not, in three-dimensional space, the Pythagorean theorem can be modified, and it still works. And it still works. Now, so on and so forth, guys, okay? So when we look at some of that stuff. See what else we could say. All right. AX, AY, you know the song and dance I just did right here. There's a theta right here. There's a lot you can say. Look at it carefully. Opposite over hypotenuse is called the sine. The sine of theta is opposite over hypotenuse. In terms of length, you're not dealing with vectors here, guys. So, the adjacent over the hypotenuse is called the cosine. So the sine is opposite over hypotenuse. The opposite over hypotenuse is the sine of theta. Adjacent over hypotenuse is the cosine of theta. And opposite over adjacent is the tan of theta. Now, that's how you get the ratios. That's pretty interesting. If they already gave you the ratio, if you already know the ratio, you can do this thing called the inverse. You can do, so let's see here. We did this. We can find the length of this thing as we said. So we said A was equal to, let me just write it over here, give myself a little bit of room. We don't have quite the room I'd like, guys, but then again, I write pretty big, so hopefully that's going to help you guys a little bit. But we got the best we can do here. We're not doing too bad. If I wanted to find what theta was, I'd get the inverse sign of the ratio AY over A. If I want to find what theta was here, I could still find the same theta, but if I got the inverse cosine of AX over A, you got this. If I get the inverse tangent of this ratio, so on and so forth. This to the negative 1 does not mean 1 over cosine. If I want to write 1 over the cosine theta, the whole thing to the negative 1 means 1 over cosine theta. I agree with that 100%. That does not equal this. That does not equal inverse cosine of something. I want to, yeah. Cosine theta, the whole thing to the negative 1 is 1 over the cosine. That's true. That's not the same as this. I don't want to put theta here, but that's not the same. They are not the same. If you want to put something like this underneath, if you want this to be underneath 1, take the whole thing and take it to the negative 1 power, and you got this. The whole thing, take it to the negative 1 power, you got this. That does not mean that. That is not this. Inverse sign is this is just a symbolism, means if I give you something, give me the angle from which it came. It doesn't mean this. This is mathematically valid. It just has nothing to do with this. This right here, if I say to you the inverse sign of this ratio, I mean this. Given this ratio, given this trigonometric ratio, given this ratio in a triangle, associated with the sine function, the inverse sign tells you what angle would give you that ratio. Given this ratio associated with the cosine, this divided by this, given this ratio, what angle would generate that kind of a ratio? What angle would generate this kind of a tangent? This is just telling, all these are the same angle theta for this particular problem, and any problem in general, but you just got to say, okay, I've got the sine function, give me the inverse sign. From what angle theta do I get this value of a sine? For what angle, put a number in here, 5. What, whatever. What, not 5 probably not, it can't work, but some other, like 0.5. What angle would give me 0.5 for a ratio? And that's the following, 30-degree angle. The sine of 30 degrees is 0.5. If this is 2, that's 1. This is the square root of 3. Square root of 3, 1, and 2. For the angle, it's a special kind of angle. We could explore it some other time possibly. But for a 30-degree angle, AY over A for a 30-degree angle is 0.5. So so if this was 0.5 right here, what's the inverse sign of 0.5? Oh, 30-degree angle. Make sure your calculator has the right settings on it. If you want the angle in terms of radians, then make sure your calculator is set to radians. If you're dealing with radians, or you want radians and or you're dealing with radians, make sure your calculator is set to radians, radian mode. If you're dealing with degrees and or want degrees, make sure that calculator is dealing with degrees. Always be aware of that. I always tell my students that as much as I can, you guys. So kind of watch out for that. So there's the inverse trigonometric functions. There's the inverse of the trigonometric functions. The inverse sine will give you the theta that would give you that value of sine. The inverse cosine will give you the theta that'll give you this particular value of the cosine. The inverse Inverse tangent will give you the angle theta that would have given you the value that was in the argument. This thing right here inside the parentheses they call the argument. Give me the value of theta whose sign value is equal to what's in the argument. Well, a sign value equal to this means that there's an inverse sign, there's an angle that gave you that sign value. Do the inverse sign on that ratio and you get the theta from which it came. Just watch out. Watch out for watch out for a lot of stuff actually, but watch out for how it's all set up. What are we talking about? Are we talking about radians? Or are we talking about degrees? So that's something that is definitely useful in this process when we're doing all this stuff, guys. See what I can say about this. This is where I love to have a class in front of me. Hopefully we'll have a class in front of us one of these days. Maybe not, whenever that is. As I'm saying this now, for the last, for much of 2020, obviously we've not had an opportunity to be together. So hopefully things change at some point. But for right now, it's good to have this stuff at least on film. And I think hopefully that'll help you guys out. So we're looking at this. Take a look at it. You see what I'm doing here. For some reason, there was something else that was kind of staying there with me. There is, I said this right here regarding, A equals the square root of the sum of the two squares, ax squared plus ay squared. Ax squared plus ay squared, that sum square rooted gives you a. And we said that came from this, and that's the Pythagorean theorem, so we don't have a problem there. Let me see what else I could say here, guys. There is, what else did I want to kind of say? I did tell you last time that if you saw what I did right here. A vector equals ax I hat plus ay j hat plus az k hat. Again, I wish we had more time. I mean, you're going to see in all my notes, there's some more complicated mathematics. It's there for you. It's there for you if you want to look at it. I don't think you need to lose any sleep on it. Just know the basics that I'm showing you. But I did provide some mathematics of physics that I think you might find pretty interesting. It's far from perfect. I don't think Sir Isaac Newton has anything to worry about regarding my presentation of things. But there's some. I quoted some brilliant mathematicians, and I looked at some of their work. I did the best I could to put some of that together for you. So there's the mathematics of physics on Canvas. And, there's other stuff. We try to solve a lot of problems for you guys and figure this out. This actually is true. In two-dimensional space, just get rid of the AZ, and you got AX squared plus, in three-dimensional space, get rid of the AZ, and you have A squared equals AX squared plus AY squared. And that's everything I was talking about right here. When I went over here, way over here, guys. That's everything I was saying right there. Here, in three-dimensional space, it works. It's not even that hard to prove it. Basically, this thing right here, any of these, you can kind of make this like a squared plus b squared. This is like b squared because this is the hypotenuse of a projection that's down somewhere. This is the hypotenuse of a projection that's down somewhere squared. Didn't we say c squared equals a squared plus b squared? This stuff right here is a lot like a squared plus b squared. Oh, that's c squared. And this is something else. This is capital A squared. Capital A squared plus c squared is equal to, the sum of those two is the hypotenuse, the big hypotenuse squared. So that's kind of the argument they got. You don't need to lose a lot of sleep on that. But it's there. It works. Stuff works. When they do this, they're saying, like I said, ax squared. There's a number of ways this stuff can get written, like I said, guys, but all right. So that's that. Now I put some stuff up here. I left some stuff up here. What is going on? Well, let me There's something, oh, okay, regarding degrees. We talked about degrees and stuff like that and a lot of other stuff. Let me leave a good amount of stuff up here and let me take a good amount of stuff off of here. It's kind of a arbitrary thing. Now, you guys, luckily, you got this on film. You can always rewind this thing. You can always rewind it and look at it again. So let me erase a good amount of stuff, leave some stuff here, and then let me talk. Okay. Okay, erased maybe a little more than I wanted to, but let me. All right, guys. I'll leave this here just a little bit. And again, there's we're not going to lose a tremendous amount of sleep on a lot of this stuff, but I at least want to give you some background on some of the stuff that's happening here, you guys. Let me talk. This thing about degrees is rather interesting. If you go all the way around a circle, here we go with circles again. You wouldn't, notice how circles are related to trigonometry. And trigonometry's got its relationship to the Pythagorean theorem, and then we get into even aspects of other things that go on. It's not just mechanical things. Mechanics, even electrical engineering is going to use circles, triangles, trigonometric relationships. Beautiful stuff. Really, really neat stuff. Basically, if you got a whole circle here, and this is length r from the center of the circle. This is length r. And this is angle theta. Well, if you go all the way around that circle, it's called one revolution. And they break up that one revolution into 360 small slices. Literally, if you had 360 pieces of pie to feed a large gathering, it's a huge, huge pie, and they say somehow we're going to be able to cut this thing into 360 equal pieces. The arc length at the far edge of the pie is going to be equal to the arc length of every other piece of pie of each one of those 360 pieces of pie. You add all those arc lengths together, you got the whole circumference of the circle. The arc length is right here. They call it S sometimes. If S is if X is 1/360th the circumference, 1/360th the circumference, and there's 360 of those, each slice subtends, or extends, I think subtends the right word for it. Each slice opens 1 degree. If there's 360 of those, you've done 1 revolution. 1 revolution is 360 degrees. Yeah, they got another thing though. This bigger angle. It's not going to be just 1 degree opening. They got this thing called the radian. And the radian is equal to when the arc length is as long as the radius is long. How many of those are in a circle? Is it true that circumference is 2 pi r of a circle? There are 2 pi radians, a little more than, about 6.28. About 6.28 radians make up a circle. A radian's pretty big. A radian's a big slice of pie because only 6 or 7 people can get fed equally. Whereas the degree, 360 people get fed, which means that each slice is really small. If you're going to get, you can get 360 slices with a degree, with 1 degree. For each one of those 1 degrees, you get 360 slices for the whole cake, whole pie. Whereas with the radian, you only get about 6 or 7, 6.5 slices. So it's 2 pi radians in a circle. S is the arc length. That right there, I didn't draw this too well, but maybe well enough. That length and that length are equal. That's a radian. That radian is when S is as long as R. It doesn't matter how big the circle is. It's about ratios. A lot of times they make it a unit circle. They make this thing R equal to 1. If R was equal to 1, what's the circumference? It's 2 pi. 2 pi radians. The radian is the arc length divided by R. If the arc length happens to be the entire circle, all the way around the circle, what's all the way around the circle? What's the length all the way around the circle? Well, the length all the way around the circle is 2 pi times R. 2 pi R is all the way around the circle. Divide by R, that's 2 pi radians. That's 2 pi radians. What if it's only halfway around the circle? Well, 2 pi radians is 360 degrees, is 1 revolution. Half a revolution is half of 360 degrees is 180 degrees. Half a revolution is 180 degrees. Half of 2 pi is pi. Pi radians is 180 degrees. So on and so forth. There's a conversion factor. If you want to go degrees from radians, you go 360 divided by 2 pi r radians. If you want to go radians from degrees, so there's 2 different things here. Well, take the 2, cancel the 2 into here. 180 over pi, degrees, radians. If you want to convert from radians and go to degrees, or if you want to convert from degrees and go to radians, so on and so forth. That allows the conversion to happen. I got to talk to you about radians some more, though. They're that important. There's a lot to say. I guess there's a whole lot to say here, guys. Let me try to say it, hopefully reasonably. This is true. What we're saying here is true. So what does that mean? It's true. It means a lot of stuff. I can invent any kind of measurements I want to measure. I can invent units of there's no end to the different ways you could construct units of measure for anything. For mass, for force, for weight, for money, you name it. For length, for height, whatever. For degrees. None of this stuff is set in stone. None of this stuff is set in stone. I can make a new degree. You know, the Malus degree, MD. How many MD? What is it? Well, the Malus degree is this. It's 100 Malus degrees comprise an entire circle. And from there we'll work with it. 100 MDs make the whole circle. Not 360 degrees, not 2 pi radians. Well, that's all. They're all true. Not 1 revolution. That 1 revolution is 100 MDs, Malus degrees. That's fine. True. True. That's just the way it is. It could be. None of these mean, you know. So there is an arbitrary nature here, guys, and we can make everything work. However, I have to say something. And that is this. The radian is kind of the most natural of all of them. Maybe there's no kind of about it. It's the most natural of all the degree. If you allow me to say, most natural, quote unquote, of all the degree measures. It's the most organic, I guess you could say, the most natural of all of them. What do we mean? Many, if not all, of the great formulas of Taylor series, when they talk about do a Taylor series expansion for the cosine function, for the sine function, for the tangent function. Let's do complex analysis using complex numbers. All of those involve the radian. All of them involve the radian. The radian, when it's a ratio like this, and what can you do with a triangle like this, guys? Well, you could do a lot of stuff. You could drop a perpendicular straight down, and you end up getting, the radius is equal, let's say r equals 1. This is also the radius. This is r equals 1. This is r equals 1. This is x. This is y. Let me play some games here. That's got a length associated with it. And let me try to, I'm not going to delve into this too much, you guys, but I think for your own personal enrichment, I think it's just a good idea to mention it, to be honest with you. You got this, and this guy comes across, it's r all the way this way. We know that's the length of r. We know that's also the length of r, which is 1. Here's x, here's y, here's r. There's a lot you can do. This radian, because it brings in the unit length of this, and it doesn't, I got to make this exceedingly clear. I could be talking about a circle that's as big as the galaxy in which we live. I could be talking about a circle that summarizes or approximates the circumference of the Earth, or I could be talking about a circle that's tiny. All of this works no matter what sizes you're talking about, because the radius and the arc length always, no matter how big this gets. I mean, in other words, you could say, okay, here's this, here's r, here's the arc length right here. Or if you made a much bigger circle, wow, it's a lot bigger, man. It's got to be a bigger, it's got to be a bigger length. This is S2. This big thing is R2. This is R1. This is S1. S1 over R1 is the same ratio as S2 over R2. Doesn't matter how big the circle is. This thing about, you could say, I could argue that with everything else. I could argue that with the stuff I made up, with the MD unit we talked about. We could do that anyway. We said that. But the big thing here is this thing. It's dealing with actual. It's dealing with actual length. It's dealing with actual length vis-a-vis the radius. It directly goes. All of these are. Man, make up your degree unit. It could be the MD unit. The XY unit, whatever units you want, the XY degree unit, the MD degree unit, the alpha beta degree unit, who cares? The alpha degree unit, the omega degree unit, who cares? They're all equally valid. You can work with them. But for this stuff to actually work, it does come down to a ratio, an explicit ratio. And the degree unit that gives you the best explicit ratio is the radian. And that's why the great formulas, Taylor series expansion for the cosine function, for the sine function, for the tangent function, has the premise that you're dealing with radians. Does that mean I can't use degrees? Short answer, not for those formulas you can't. You got to convert the degrees to radians. It can be done. If I know any kind of degree, they have an equal validity with all other degrees. But to make those formulas really be, to really be able to utilize those great formulas for the Taylor series, you're going and using radians. There's a thing they use, and I don't want to beat this thing into the ground too much, you guys, but there's many of you, those of you who have the calculus background, because I'm giving this to two different classes, or a lot of them. I'm going to try to give it to different people. Some people have the calculus background, some don't, depending on what course you might take with me. I think this stuff might be of use if we look at it. That is the square root of -1. And how on earth, yeah, even here, electrical engineering uses this formula too. You can do a lot with that formula. How you're going to look at it, that's another matter in its own right, I guess you could say. But what it means, there's a lot of application here, man. E to the I theta equals cosine theta. E to the I theta equals cosine theta plus I sine theta. I can derive so many things in trigonometry from that formula. It comes from the number E, one of the most fascinating numbers in mathematics. A great mathematician, I think Walter Rudin was his name, he taught at Madison for a long time, said that the exponential function, that is the exponential function, it's e to the x. E to the x, e to the z, if you want to put complex numbers in there. E to the x or e to the z if you want to put complex numbers in there. The exponential function Dr. Rudin called the exponential function the most important function in mathematics. It's hard to argue against him. It's hard to argue against him regarding that. If we took the number E, which is fascinating in its own right, it's a beautiful derivation of it, beautiful discussion of it, not our business right now. But the number E behaves in a fascinating manner when things are being exponentiated. When the quantity is being when E is being exponentiated, it behaves in a fascinating manner. For our purposes, there is an expansion. There's a great mathematician, Ivan Sokolnikov. He also taught at Madison. He taught at UCLA. He wrote a pretty classic book. I try to use some of his work when I was doing some of the mathematics of physics to give to you guys and stuff like that. To the best of my ability, I tried to put some stuff in there that was manageable. It takes a lot longer than we have time to do, guys. But Sokolnikov knew what he was talking about. Rudin knew what he was talking about regarding this stuff. Sokolnikov was saying he gave some pretty fascinating discussion pertaining to the number E and how it behaves. Usually we're used to the number E being e to the x, some real number. That's certainly true, and it works. You could put anything in here, just about. I mean, I don't want to never say never, never say always, but there's a tremendous amount you can put in there. You could put straight out complex numbers in there. A plus bi on top. You know, instead of I theta, this whole thing could be e to the a plus bi, and let's see how it all plays out. You know, I'd have to take a look at this and analyze this a bit and see how we're going to define what you define. That's neither here nor there. For our purposes right now, theta is real, theta is real, theta is real, I is imaginary. But that E, you could put anything in there. You could put complex numbers on top. I'd have to look at this, see how it behaves when I do something like that. It's another story. But you could definitely, I could put e to the z is e to the a plus bi. A and B are real, I is imaginary. And then see how this whole thing plays out. We could do a whole lot of analysis here. The big thing is, guys, there's this thing in mathematics that Dr. Sokolnikov talks about. He wrote a book in 1939. It's still a classic. You know, it's about advanced calculus. But there's this thing they call in this other book he written with a guy named, I think, Redheffer is the name. Redheffer and Sokolnikov had written some stuff in the 1960s too. they have this thing that's called analytic continuation. Analytic continuation means you can put other quantities that you normally do not see or that you're not used to seeing in a particular function, and you can see how it behaves. That's kind of what's going on here. They're putting stuff in here that normally does not occur, or we're just not used to seeing it normally in most circumstances, and yet it works. There's stuff you can do. There's mathematical application. To what? To aeronautical engineering, to electrical engineering, to a whole bunch of stuff. Say, wow, you're dealing with complex numbers and you're answering these real life questions? Yeah. Analytic continuation with the mathematics. It's math. There's a lot of mathematical validity at which we can arrive if we use other quantities that we're not used to using. Is there a consistency? And the way they're actually able to, for this example, do something like this, they look at the expansion of the exponential function in its Taylor series, and they plug in I theta, and it resembles, not just resembles, it is this when you're looking at individually the Taylor series for the cosine of theta and the Taylor series for the sine of theta, and then multiply by I. When you multiply the Taylor series for the sine of theta by I, when you multiply the Taylor series for the sine of theta by I, you get something. Cosine of theta, leave it as something. When you add them together, you actually get this. When you plug this, the I theta, into the function e to the x equals 1 plus. Let me try to x to the 1 over 1 factorial plus x to the 2 over 2 factorial plus x to the 3 over 3 factorial. You get the picture. This goes on forever. It's convergent. There's a lot going on. I mean, you go to here. And they're saying if you put I theta into here and put I theta here, put I theta here, etc., it spits out, according to Taylor series, something like that. Crazy stuff. The way the function here, the way the exponential function, generally speaking, behaves, regardless of whether you have real numbers in there or complex numbers in there, regardless of what you have in there, the way the complex function, the way the exponential function behaves, regardless of whether you have real numbers in there or complex numbers in there, the way that the exponential function behaves when you are exponentiating and doing other stuff and doing other things is absolutely fascinating. Beautiful mathematics pertaining to it. You would use the multinomial. I have this in the mathematics of physics a little bit, not much. I just talk. I point to the direction that can get you there. But through use of the binomial theorem and generally through use of this other theorem, which is more general than the binomial theorem, called the multinomial theorem, and it answers this. It answers this. When you use the multinomial theorem, this stuff is provable. Not particularly very difficult, but very tedious. So much of this stuff is tedious. But anyway, something to look at. But this right here, you guys, this formula lets you get away with all of trigonometry. Pretty crazy stuff in that regard. Okay? Now, let me think here, guys. We said a bunch of things here. Let me stay. I know I left this guy here. I left him here for a reason. Let me just say a couple things on it. I can't get overly crazy with it, but I'm at least point to some things that go on here. And I think it's going to help us when we do a lot of this stuff. Okay. So if this is the case, again, you always got the rewind button. So, I mean, we look at it that way. So let me get rid of some stuff. Let me leave that there. Let me talk about a couple other things. And then let's talk. Okay, one of the big takeaways of a lot of takeaways here, I think, is how natural the radian is. How the radian lends itself to a lot of stuff that goes on in mathematics. How you want to look at something, how things relate. How things relate. To find the derivatives of various things involving trigonometric functions, the radian is key. It's really the most natural, as I said, of all of those. But all of the units, made up and otherwise, I mean, they're all kind of made up. It gets into a philosophical issue in its own right. What's the nature of language itself? Is it made up? You know, a lot of people will tell you that it is. You know, but we got to be consistent though. We got to agree on what we're saying. That's for sure, made up or not. So you got something like this. They've got a thing. When you're trying to find like the work done, you got a thing called the dot product. That's down the road. I don't want to get, I don't want to jump the gun too much here, you guys. But basically, they got this thing called the dot product, and it's basically this. Here's two vectors in three-dimensional space. If you were to go A vector dot, solid dot, A vector dot B vector, this is kind of nuts. I wish I had, actually I do actually have it. See which one I'm going to use here. Let's say this is A vector. Let's say A vector is the longer of the two vectors. Say my hand is at the origin in three-dimensional space. It's an arbitrary origin, but it's independent upon where things are located. It's always going to work. You're always still going to get the same answer. Okay? So let's see here. Let's see what we can say here. This is a vector, this thing. Vector A, vector B. Here they are. One fires out this way, one fires out that way. There they are. I can increase the angle between them. I can make it look like that. Decrease the angle. Heck, I can move them around too. I can make them go in that direction. Any direction you want. This way, that way, you name it. Okay? So these A vector and B vector. The dot product of the two vectors, by definition, is equal to how big is A, how big is B. Now remember what we said. We already said this. I mean, we said that the magnitude of A vector is A. The magnitude of B vector is B. Okay. It's the product of the two vectors times the cosine of the angle between them. There you go. There's a 30-degree angle between them. There's a 45-degree angle between them. This is 10 meters. This is whatever. This is 10 units long. This is 3 units long. 10 times 3 is 30 times the cosine of 30 degrees, or the cosine, let's say there's a 60-degree angle between them. There's a 60-degree angle. The cosine of 60 degrees, right? The cosine of, that's pi over 3 radians. The cosine of pi over 3 radians is the same as the cosine of 1/6 of a revolution. 1/6 of a revolution is 60 degrees. 1/6 of 2 pi radians is pi over 3 radians. They're all the same. The cosine of pi over 3 radians is the same as the cosine of 1 revolution divided by 6 is the same as a 60-degree, the cosine of 60-degree angle. They're all the same. This is a 60-degree angle. The cosine of 60 degrees is 0.5 times 3 times 10. 3 times 10 is 30, times 0.5 is 15. That is the that's the dot product. It's A times B times the cosine of theta. Here's the crazy thing. You can prove through some beautiful mathematics that's not particularly very difficult, but is very tedious. As in so much that we do, guys, you know. Believe it or not, doesn't look like it. It looks like it's some kind of a joke, maybe. I mean, some people might think, and it's like, wow, is that just made up or what? I mean, what's going on here? If you take the x component of A and the x component of B and multiply them together, and then take the x component of A, the x component of B, multiply them together, and multiply, so A sub x, B sub x, x component of A, x component of B, multiply them together, add that product with the product of the y component of A and the y component of B, add that with the z component, the product of the z component of A and the z component of B. Add these together, it's the same as AB cosine theta. Believe it or not. It's a way to prove it. Great mathematics to do, guys. Again, this is the kind of stuff you just wish you had a lot more time. Sometimes teaching these classes, you'd almost wish you could have a whole year. For each of the one semester classes, you wish you had a year of it. You know, I mean, I think you guys would probably, I wouldn't blame you if you didn't want it that way, because you gotta get through the school too, you know. But wish we had a little more time. You know, it's obviously we do some of this stuff. But that's some of this. This is a dot product. That's a magnitude. We just said it's a magnitude right here. A is equal to the magnitude of A. Just A like this is the magnitude of A vector. B is the magnitude of B vector. A magnitude times a magnitude, a scalar times a scalar is yet another scalar, times the cosine of theta, that's a scalar as well. AB cosine theta is a scalar answer. They use this stuff a lot when you're talking about energy, work. How much work was done? Well, the angle, I pushed at this angle and I moved it over a distance. And we'll talk more about that, but that's a dot product. That's a dot product. So we got something like this. That's basically a dot product. And then there's ways to get around that as well. They got this other thing where that dot product is a scalar quantity. And it gets used when you're calculating work. That's one big place it gets used when you're calculating work. They got this other thing when you're calculating torque and stuff like that. You want it to be a vector quantity. You could have a vector cross, like an X right there, cross. A vector cross B vector, that's another vector. That's another vector. And the order that, notice guys, here, the order that I do the dot product, doesn't matter. A vector dot B vector is the same as B vector dot A vector. All I got to do is switch these two around, and by the commutative property, there's not going to be any difference. Here it does matter for the cross product that I'm showing. The cross product is a right-handed system. Let me write it down a little bit and let's see what we can say about it. If you wrote down let's say, A vector looking like this, and you had B vector looking like that, this is the angle theta between them. This is kind of crazy stuff. Let's go into three-dimensional space. Let's say somewhere in three-dimensional space, there's A vector, there's B vector, and I want to do A vector cross B vector. When I go, and again, a lot of this stuff, you're going to be able to get around it. Even in my calc-based classes, you can kind of get around this stuff. They're not going to hit you real hard on it, but in the non-calc, they're not going into this, I don't think, at all. So, but still, it's there for you for your personal enrichment when we're doing some of this stuff. But for calc-based, I mean, this stuff is fair game. Fair game. A vector, B vector, it's a right-handed system. Why is it a right-handed system? Because they made it up that way. They could have just as easily invented a left-handed system. We drive in a right-handed system, arguably. What side of the road do I drive on? On the right side of the road. What side of the road does the other person drive on? Yeah, hopefully they're driving on the right side of the... Relative to me, I'm driving on my right-hand side. The other person on the other side of the road is hopefully adhering to the same rule and driving relative to him to his right-hand side. Hopefully everybody's driving on their right-hand side. Somewhere else, if they're choosing to drive on their left-hand side, which is true, hopefully everybody's agreeing to that. This is a vector. This is a vector. This is a vector. This is B vector. You take your right hand. It's made up. It's made up. But they say, okay, if it's made up, it's made up. You take your right hand, you take your fingers of your right hand, and there's other ways you can do this, but this is the way I always teach it. It's not the only way. Take the fingers of your right hand and point them in the direction of A vector. Point the fingers of your right hand in the direction of A vector, and then roll your fingers toward B vector. Your thumb points outward perpendicular. That right there is A vector cross B vector coming right out at you. It's perpendicular to the two of those, and it's equal to the product of the two of them times the sine of theta. So A vector cross B vector is another vector. The magnitude of that, I'm saying magnitude, that's just as big as A times as big as B. Take the size of A, take the size of A, the size of B, multiply them, and multiply by the sine of theta. This is useful when you're dealing with torques. The other one's useful when you're dealing with work. But this has utility. There's stuff that happens in nature that the scientists encountered certain things in nature where they saw and say, okay, I'll tell you what. Can we figure out some mathematical relationship here? And that's what they did. They looked at how things behave, how a particle behaves in a magnetic field, how a charged particle behaves in a magnetic field. It behaves according to that. It behaves according to that. Yeah, great. How? So, I mean, basically, guys, I want to make this clear. I mean, if this is A vector, what's in my hand, and this is B vector, if I'm going to cross this, I'm going to cross right hand, fingers right hand, roll, my thumb comes right out. My thumb comes right out that way. So what you end up having is, this is, I don't know, guys, let me go A vector. Let me make this one with black color, this one with green color. Let's have it here. Let me roll it. I'm going to roll here, roll that way, bam, comes out here. What if these guys are located that way? Oh yeah, everybody moves. Roll him, goes like that. Roll him, he goes like that. Look how he's going. It's always according to something like that. Okay? So on and so forth. So, okay, great. Believe it or not, if we're located, believe it or not, if we're located like that, roll the fingers of your right hand, go this way, bam, it comes out here. I can find the coordinates of the endpoint at the very tip of that vector. I can find the coordinates of that vector. I can find the coordinates of that vector at the very end of that, if I know the coordinates of these vectors. There's some beautiful mathematics that gets involved in that, just like there was beautiful mathematics involved right here. In both circumstances, it's not incredibly difficult, but they tend to be very tedious. Everything I've talked to you about, if you're going to prove it, is not incredibly difficult, but it is very tedious. It is very tedious, that's for sure. So what's going on here? Well, I just said it was tedious. I'm not going to, drive you too crazy on it, but just for the standpoint of of talking about this a bit. A vector cross B vector is equal to, if you guys know determinants, here's an I hat, here's a J hat, here's a K hat, and go AX, AY, AZ, BX, BY, BZ. Evaluate that determinant. It's not really a determinant, but what the heck? It kind of behaves like, we can make it behave like one. The end of the day, man, how do you do a determinant like this? Well, row 1, column 1, row 1, let's go right for this guy. Row 1, column 1, row 1, column 1, 1 and 1 is 2, is even. This is going to be I hat, go here, AY, AYBZ, AZBY, and there's a lot of ways to write this. Let me try to give myself enough room here, I guess. Guys, I'm already kind of foreseeing there's going to be an issue with the room, maybe a little bit. Let me write this somewhere a little bit further over. AYBZ minus AZBY. So that's this guy, and that's going to be AYBZ, this, AYBZ, AZBY, minus, why am I saying minus? Well, I'm going to say plus. How about I say plus a negative then? Why am I even saying that? Well, let's take a look. Row 1, column 2, row 1, column 2, 1 and 2 is 3. It's going to be a negative. So plus a negative. And here we go. AXBZ minus AZ BX. And I'm still about to run out of room, guys. All right. So I'll write it there. I'll write it here, and I'll write it somewhere else too. Let's go to K. Row 1, column 3. Row 1, column 3. 1 and 3 is 4. That's going to be K vector. And I'll write this again, guys. I mean, that's AXBY let's see here. Let's just make sure I got that right. AXBY, AYBX. All right, let me write them. Go somewhere here and write it. Should give myself. Never went far enough over, guys. But then again, so you see that there. So let's see here. All that whole song and dance. And let's just see here. Let me just write it here. And if this doesn't work, I'm going to go in the hallway and write it. Just kidding. All right, that's a lot. You don't encounter this in our course a tremendous amount. Something higher course you would. Either one, in the 209 or the 120 course. And like I said, I'd like ideally, I'm hoping people can look at this from either course and they may hopefully get something out of it. What is going on? There's a lot here, man. The AYBZ, AYBZ are just regular numbers. They're scalars. As is AZBY, regular numbers, scalars. Product, scalar answer. Scalar answer. Subtract, scalar answer. Same exact thing going on what's in here, guys. These are where the vectors come in. Believe it or not, A vector cross B vector is going to be a vector that looks just like this. It's going to be, remember how we did that? I mean, there's one guy, here's one of them. Here's A vector. Here's, let's say, B vector. And the other guy, here's theta between them. And bam, it pops out. It pops out looking just like this. How big is it? Even though it's a big mess, it's as big as the product of the magnitude of A and the magnitude of B. The product of the magnitudes of A and B times the sine of theta between them. The product of the magnitudes of A and B times the sine of theta, the product of these two magnitudes, A and B times the sine of theta, will give you how big this thing is. What are you talking about? Are you telling me if I squared this, and squared that, don't worry about the K's, the J's, and the I's, just square all of this in here, square all of this in here, square all of this in here, add them together, get the square root. It's as big as the magnitude of this, which is ax squared plus bx, which is ax squared plus ay squared plus az squared, and as big as the magnitude of this, which is bx squared, by squared, bz squared, square root of that, square root of the magnitude. You get the magnitude of both those, multiply them, you're going to get that answer. You don't need to lose a whole lot of sleep on this, but there's a proof that actually this tells you where it's located. To me, that's crazy. You're telling me you could put any two vectors anywhere in three-dimensional space, and I can get their cross product, and I'll tell you the coordinates of the endpoint of their cross product. What does that mean? The coordinates of the endpoint of their cross product is telling you how big, it's telling you what the name of the vector is. It's telling you where the tip of the vector is located. This is what the vector is. I could tell you what the vector is based on this mathematics that you give me. It is a complicated story. Not incredibly difficult, but quite tedious. And it behaves according to the right-hand rule. The crazy thing about it is, this thing pops out of there according to the right-hand rule. What would happen if you changed the direction of these? What would happen if you put the B vector in front and the A vector here? Then you'd have to change these two. And everything would be the same, but this guy would be in front of that guy in back, this guy in front, that guy in back, this guy right here in front, that guy in back. Same exact magnitude, but diametrically different direction. Exactly opposite direction. All of it's very provable. Not our business right now. I don't even have that in the mathematics of physics when I put it in there. I probably could have put it in there, but it's there. This stuff can be proved. That's, again, I wish we had more time. But anyway, this is what we're talking about regarding some of this stuff, you guys. I think this tells us a lot. I mean, this not only tells us a lot, it likely tells us more than we need to know. But that's good. I mean, I'd rather we err on the side of caution. And down the road, if you want to get serious about this at a higher level, some of the start to that process has been given to you right here a little bit. At least we're pointing to it. Beautiful stuff, man. Some great stuff. Simple as that. See what we can do here. see what we can do with some of these problems. Okay. Let's talk a bit more. So, for chapter 2, problem 30, so we got problem 30 here. Now let's take a look. Again, this is the Katz book, guys. So we got here. They talk about a few things, and I think we again this predominantly, guys. Anybody who's going to watch this, please. I mean, everyone's welcome to watch this, and we'll see what they allow. For whom I think it's anybody can watch it. But for you guys in my 209 class, some of this stuff flat out is to be safe. Know all of it, or know as much of it as you can. For Physics 209. So at the 209 aspect, calc-based treatment, problem like 30, we got to know it. Simple as that. So chapter 2, problem number 30, they're talking about, and you guys have reference to it that have the book and stuff. Obviously, we need to be looking at it. For problem number 30, the instantaneous speed of a particle moving along one straight line is v of t equals at e to the negative 5, where the speed v is measured in meters per second, the time t is measured in seconds, and the magnitude of the constant a is measured in meters per second squared. What is the maximum speed expressed in multiples of a? So basically, you guys, I mean, let's take a look at it. Again, you got the best way to do this is have the book with you, you guys. Obviously, have the book and be looking at this while we're talking about it. So what we got here is the instantaneous speed of a particle moving along one straight line is v of t equals at e to the negative 5t, where the speed v is measured in meters per second, the time t is measured in seconds, and the magnitude of the constant a is measured in meters per second squared. What is the maximum speed expressed as a multiple of a? Okay, stuff's a little probably somewhat easier. Many of these things, guys, not to worry. I mean, they're easier done than said. Let's talk about it. Well, we're trying to find, they're looking at this thing and they're trying to find, what is the maximum speed and everything else associated with it. So what you can say here is they are v of t, we'll say v. It's a v of t is equal to a function. We'll call it v. A is some kind of a constant. T is time. E to the negative 5t. This is kind of a loaded statement, guys. I mean, usually for this to make sense, this is fine. Mathematically, there's nothing wrong here. But you got to be really careful. And that is, let me see here. Am I here again? All right. Okay, guys, see me if for some reason I'm having a little bit of an issue with the recording. Okay, it's going okay. All right. Okay, let's keep going. We got this right here, you guys. This is all good, This is actually fine. Just to make sure everything's okay here. We can see it okay, right? Doing good? All right, yeah, fine. This doesn't have good meaning for it. Mathematically, you can do a lot of stuff, so we're not going to worry about that too much. But for our purposes in physics and the real world kind of thing, this e to the negative 5t has got to be a real number. Or at least, it doesn't even always have to be a real number. I take that back. But the stuff on top, the negative 5t, has got to be something where it's unitless. So that when I hit e to the negative 5t, it somehow just gives me a regular behavable answer. That 5 is something probably in inverse seconds because the t is in seconds. So you want it to be unitless. Otherwise, it doesn't make any sense for our purposes. I don't want to split too many hairs on that, but let's see what we got here. For a maximum or a minimum, dv dt equals 0. True. Well, go for it then. Go dv dt. Do dv dt right here. You're going to have to use the product rule. You've got this function and you got that function, and there we go. We're going to do the product rule. First guy is, this is f, this is g, this is f prime g plus g prime f. If you grind it out, it comes out to there. Okay? The way it really comes out is, you want to go g prime f, it's coming out, or f g prime, here's f, and the g prime is negative 5. So we're doing that. At the end of the day, you got to set it equal to 0. You want a min or a max. They're asked for a maximum. Move this around, guys. Figure out what's going on. You got this. If that's the case, add the opposite of this on each side. Set them equal to each other. Well, it doesn't matter what time you're talking about. E to the negative 5t equals e to the negative 5t. It's the same in both circumstances. It's the same in both circumstances. So, let's see what we got here. Divide by e to the negative 5t on each side. Divide by a on each side. Solve for t. Let's go. Plug in what you got to plug in. You got v is v. This is the original function given to you. Go back to it. Go back to that original function. And do the math. Plug in. Well, what's going on here? Well, there's a lot going on. We found. Let's try to figure out where. Yeah, right. Okay, so we said t is 1/5 of a second. So let's write it in there. T is 1/5. A is a. T is 1/5. We got this. A. This is e to the negative 1. V. E to the negative 1 is just 1 over e. So we've got v equals 1 over 5e times A. That's fine. Usually they want more specific answers. You know, like I said, you got to watch out how they want the answers too, guys. I hate to play that with you, but 1 over 5e, and that's and there it is. You can write it like that. What's the velocity in proportion to A? Or in regards to A, the maximum velocity, 0.0736 A. Okay? So that's that. I mean, that's for 2. That's 30. Let's look at 56 and 57. Let's go to 56. 56 and 57. Let's see where we're going to go. For 56, let's read it. 56, the engineer of an 56. The engineer of an intercity train observes a rock slide blocking the train's path 225 meters ahead and activates the train's emergency brakes. The train decelerates uniformly. The train decelerates uniformly at 1.8 meters per second for 12.70 seconds before reaching the rock slide. What is the speed with which the train reaches the rock slide? Okay. There's stuff going on. Stuff going on again. All right, we've talked about a number of things. Let's talk some more. They're getting into some stuff here, so I might as well, within the context of doing the problems, I think we can do a lot of discussion, a lot of lecture. I think it's one's not apart from the other. It's like saying communicate by delivering a speech, but don't show up and don't talk. You know, you can't do that. You got if you're going to talk about something, if you want to talk about solving some of the problems, you want to explain why the problems are what they are, how things work as they work. Okay. With that in mind, let me say a few things. And we can kind of take it off from there. All right, guys. There's a lot can be said. Like I said, I'm going to have to. I think the intelligent way to do some of this stuff is leave some of it to the. I'm going to leave some of it to the book too. To try to do it. It's an argument as to where you're going to go. You're obviously going to be reading this book as much as possible, you guys, when you're doing this stuff. And then we take it from there. The more you're reading the book, guys, the better off you are in this stuff, and I'll try to give some explanation as to what's going on here. Tell you what I'm going to do. Let's take kind of a real gut feeling look at some of this stuff. I think it helps us, and then we can get into more specifics later on. You don't want to be blinded by the forest, nor do you want to be blinded by the trees. I'm going to try to make this reasonable. I don't know how good of an analogy that is, but let's take a look here. If you want to talk about distance traveled, let's talk about a straight line. I know there's a lot of ways to look at a lot of things. Right now, let's just kind of keep it simple and kind of move from there as we need to move from there. And you're also reading the book as well, so I think we're going to be okay. We are in the situation that if you took, that's not a vector right here, that's average. If you took the average speed, speed's a scalar, velocity's a vector. Sometimes they get used interchangeably, but they're not interchangeable. Through various slips, hey, high velocity impact, high this, that, yeah, whatever. It means high speed, usually. For our purposes, we're not worried. You know velocity's a vector, you know speed's a scalar, and so how things get interchanged in colloquial language, that's not going to bother us. We know velocity's a vector, we know speed's a scalar. D is D. V bar means the average speed. If you got an average speed traveling, and you travel for a time t, average speed times time gives you the distance. If the acceleration is uniform, take the final velocity, take the initial velocity, or take the initial velocity and the final velocity. Doesn't matter the order you add them. Take the final, take the initial, add them together, divide by 2, multiply by t, and you'll get the distance. Fair enough? See what else we could say here. Is it true acceleration is the change in velocity? I'll say change in speed right here because it's only in a straight line, so it doesn't mean a big deal. I'm going to use velocity and speed interchangeably sometimes. We already talked about, we know the subtleties. The difference in velocity the difference between final velocity minus initial velocity divided by the time where that change took place, that's acceleration. If you multiply by t on each side and divide by a, multiply by t on each side and divide by a. So in other words, I can find acceleration from this formula. I can find time that it took for the acceleration to take place from this formula. If I multiply by a on each side and add a vi, I can find the final velocity from the initial velocity, the acceleration, and the time over which the acceleration took place. All three of these equations, each one of these three equations is born from the other two. Put another way, any one of those two equations is born of the third equation. These two came from him. If I want to use this one, I can get these two. If I want to use that one, I can get these two. If I want to use this one, the original, I can get those two. They're all the same equation in a sense, just all written in different forms from one another. This is pretty interesting stuff. I mean, because later on, when we deal with rotational motion, we're going to use this stuff again. It's not really that far off. Not far off at all. All right. Let's see what we can say here, guys. We know that D is, well, there's a lot of ways you can do it. We said that D was this. VF is VI plus AT. That's what VF is. VI plus AT. VI is VI. Did we say the average of these two? Yeah, we kind of did a gut feeling argument so you could do that. What's going on here? We've got VI and VI is 2VI. AT is AT. Go here, go there. 2VI divided by 2 is VI. 2 into here multiplied by T on the outside of all that. Bring the T Absolutely. Absolutely. Absolutely true. Okay. Something else we can say about this? Yeah, I think so. I think we can argue this another way too. And this is going to be useful later on. We're going to get into rotational motion later on, and the exact same equations are going to be in play. The names are going to be changed to protect the innocent. It's like from the old classic TV series, Adam 12 and Dragnet and stuff. And I can change some of the names on what's going on there. The mathematics is identical. The mathematical processes are identical. We'll see that when we get into rotational motion, how that all plays out. So let's see what we got. So is there another way out of this thing, and why do we want another way out of it? Well, I mean, the more ways we know how to do stuff, guys, oftentimes it's going to help us. I mean, we're saying this. We're saying that's this. It doesn't matter if the VI or VF is in front, but there's a reason why I'm doing it, and hopefully it's convenient for you later. I got something to ask you. I'm not going to change the VF and VI. I changed it earlier and made the VF VI plus AT. Now I'm not doing that. I'm going to change the T. I'm going to change the T. VF minus VI over A. Forgive me. That's this right here. I mean, they're all useful. Right there. Right there. Why don't you take this guy, put brackets within brackets or parentheses within parentheses. VF squared minus VI squared over 2A. And that ends the story. There are two different equations to get you the distance traveled, associated with an initial velocity, a final velocity, a time, an acceleration, associated with something there. I may not know, if I know all four of those, if I know V sub F, if I know V sub F, V sub I, if I know V sub F, V sub I, A, and T, well, I'm pretty much set. I know just about everything I need to know. Getting D is pretty easy. But if I'm looking at D, V sub F, V sub I, you don't need all of those to get, of those five, you need to kind of figure out some way. There's distance, there's V sub F, there's V sub I, there's A, and there's T. There's five unknowns. I mean, if you know all five of them, there's no point in asking the question. You just know what you need. But if I know four of them, even three of them, I mean here, well, yeah, even three of them gets me there. If I know VF and I know VI and I know A, if I know those three, bam, I can get this. If I know VF and I know VI and I know A, I can get T. I can get the fourth one. So if I got 3 of them, there's stuff of the 5, as we said. Distance, final velocity, initial velocity, acceleration, and time. Those 5 things. If I know 3 of them, I'm probably okay. If I know these 3, I got that. If I know these 3, VI, T, and A, I can get the distance. If I know VF, VI, and A, I can get it. So this is what's going to get us to a lot of places we need to go. Later on, as I said, when we get into rotational motion, remember these, remember them well, because rotational motion is going to look a lot like what's going on here. Let me think. So what do we got here? The engineer in an intercity train observes a rock slide blocking the train's path 225 meters ahead and activates the train's emergency brakes. The train decelerates uniformly at 1.8 meters per second, 12.70 seconds before reaching the rock slide. What is the speed with which the train reaches the rock slide? Okay. Note, this equation holds only for constant acceleration. So how are we going to do this? You could go a whole bunch of ways. I do have it in the notes, you guys. I just want to make sure I can don't want to drive you too crazy with it. Just got to make sure it's got to be reasonable at some level. What is the final velocity? Now, this is a rather interesting situation. They're asking, what is the speed with which the train reaches the rock slide? Man, that's a euphemistic way for saying how fast is the train going when it collides with the rock slide. It sure looks like it. That's how fast it goes when it's reaching it, right? So I don't know. What's the ideal? The ideal is it's already stopped a couple meters before it hits the rock slide. 5 meters before it hits the rock slide. Or it stops right just before it was about to hit the rock slide. I don't know, maybe that happens, maybe that doesn't. Let's try to figure this out. They're not saying a whole lot here. They're giving us, they're telling us some things. They're telling us the acceleration, the time, a whole bunch of other stuff, but not other things. So how's this going to play? Well, we already know all this stuff. I tell you what, let's find out how fast this thing's going. See, they told us we got to figure out how fast it's going at the end. We got to find what VF is. We have to find what VF is, you guys. And so let's see what we can say. The thing with, we got to find VF. Well, I'll tell you what, it's hard for me to find VF when I'm not even sure what VI is. I do know this much. It's going to reach the rock slide in time t. So I'll tell you what, I'm going to go right here. And do you agree? Right here, let's go with this guy. The rock slide is 200, just go right with this guy. Rock slide is 225 meters here, 225 meters away. I don't know how fast it's going initially. I do know that it went for 12.7 seconds. It reached it in 12. I'm not telling you how fast it's going. I'm hoping it's not going fast. I'm hoping it stops. I don't want to hit the train. You don't want to collision with the train, but it's an experiment. It's a train. It's automated. Nobody's there. Nobody's in there. Let's see what happens. How fast is it going if it does collide? It went 225 yards. Initially, a speed VI, it covered 225 yards in 12.7 seconds. The brakes were on the thing. The brakes were on this thing, which meant it was negative 1.8. You got that? Well, whatever. The rest is math, guys. I'm going to get that all by itself, is what I'm going to do. I'm going to take all of this, and put it over there. I'm going to add the opposite of this quantity, put it over there, and divide by 12.7. Getting everything over to one side and you divide by 12.7, you got there it is. Yeah, there it is. VI. Now, I don't even think they asked us this, to be honest with you. VI equals 29.15 meters per second. You know what? It's a good question to ask. It's a great question to ask. I don't think they went there, but they could have gone there. They could have, hey, by the way, how fast was this thing initially moving? If in 12.5 seconds, if in 12.7 seconds, how fast was this thing moving? If in 12.7 seconds it went 225 meters, with a deceleration going on of negative 1.8 meters per second. Acceleration of negative 1.8 meters per second, which is a deceleration. Well, what's VF? There's a lot of ways you could play it at this point, guys. One, two, three. What about that one? VF. How fast is it going? I think it's right there. You could. The way I don't know what the way I solved it. You could have solved. You could do a whole bunch. I solved it in my notes. I solved it differently. Yes and no. I solved kind of the same thing, but I'm not going to be. This is to me a little more straightforward. What I'm about to show you. My notes are fine. Either way you want to go, use that. How fast is that thing going? VF equals VI plus AT. Here it goes. Let's find VF. VF they did ask. They didn't ask what VI was. I did it a little differently in my notes, but that's no big deal. VF is 6.283 meters per second. How'd they get that? Actually, that's a good question. Well, we got 29.15 right here. That's VI. Acceleration is negative. Negative 1.8 times 12.7. Grind out the math, you guys. This thing ain't accelerating. You don't put the brakes on and have your thing accelerate. That's not the kind of brakes you want. And there it is. I did it a little differently, not much. It's essentially the same mathematics. This is just a lot more straightforward. When I did in the notes, I should have gone right this way. I essentially did the same thing, but it's a little bit different. But this is fine. Either way, you can look at it, guys. You got to make this make sense to you. Okay, it's got to make sense to you. So that's the situation there, you guys. And that was problem number 56. I hope I wrote that down somewhere. That was 56. I'll put it right here. And that's 56. Okay. Let's go to 57. All right, for 57, all right, guys, forgive me, I'm getting out of the picture here. Maybe I can move this stuff later on a little closer. 57 is saying a pebble thrown downward from a 44-meter cliff with an initial speed of 7.7 meters per second. How long does it take the pebble to reach the ground? Pretty straightforward. All right, let's take a look at it. That's 57. So there's a lot of looks here. It's good that we're leaving a lot of this stuff up here. Let's see. When we run out of room, we'll erase, I guess. All right, guys. So 57, what's going on here? I mean, there's a whole bunch that goes on. They want to know how long it takes to hit the ground. Tell you what I'm going to do. Tell you what we're going to do. For 57, I'll write it here as well, man. Compensate for what I did last time. Didn't write it down initially. I think I'm going to work right here. Look, I can't really do. There's a lot of ways to go here. There's no time in this particular equation. So I'm solving for time in an equation that has no time. It doesn't work. I have to use an equation that does have time. Okay. Other equations have time as well, but they're not giving you enough data. Though that's, you can't really get yourself out of the woods too easily on all these. You're gonna have to come here. You're gonna have to come here, you guys, to this guy. What's going on here? Well, the thing fell. The thing is being thrown. Let's see what we got here. The thing is being thrown 44 meters down. From a 44-meter height, it's being thrown. The initial velocity given to it is downward at 7.7 meters per second. I don't know how long it's going to take for that flight to happen. That's, I guess, what I'm trying to find out. 9.8 meters per second is the acceleration due to gravity. If ever they throw something at you where they throw something upwards and then it's got to come down, you always use G as negative. Negative 9.8 meters per second. Treat downward, below, as a negative number, upwards is a positive number, acceleration is always negative. If you're starting from somewhere high up and you throw something down, even though everything is negative, including G and including the distance is a negative distance, the displacement's a negative displacement, and G is a negative number. If they're all negative, you can call them all positive. So it's not a big deal. When there's a disparity, however, there's an up and there's a down. Above ground zero and below down zero, always treat G as negative. Always treat G as negative then, if that's the case. Just make sure that you're agreeing with what you're doing. I mean, you're agreeing with yourself, you're agreeing with the units that are supposed to be going on here. This is it. This is it, guys. Ladies and gentlemen, that's it. That's what you're going to do. Do you guys remember that ax squared plus bx plus c equals 0? X equals the opposite of b plus or minus the square root of the quantity b squared minus 4ac You remember that? We remember this right here. So we got this. Let's talk. I mean, go some more. I mean, this is 44. This is 7.7 t. This is half of this is 4.9 t squared. So what is going on here? Yeah, what's going on is we're going to do the setup on this thing. Why don't you subtract 44 on each side and set the whole thing equal to 0 and let's see what's going on here. So let's see what we got. Okay, we already said if you got ax squared plus bx plus c equals 0, x is going to equal the opposite of b plus or minus. It's two solutions here. Doesn't mean both solutions are good. Hopefully one of them is good. X equals x equals the opposite of b. X equals the opposite of b plus or minus the square root of the quantity, the square root of the entire quantity, b squared minus 4ac. The entire quantity, including the negative b, is over 2a. Let's go. Let's add a negative 44 on each side and do a setup here. There it is. A is 4.9, B is 7.7, and C is negative 44. You're going to put all of that right there. Yeah, absolutely. T equals negative 7.7. Look. Here it is. You got B, B is 7.7, A is 4.9, and C is negative 44. .9 for A, C is negative 44. for 2a. 2 times 4.9. There it is. Well, when you do it, you're going to get, you're allowed to, you're allowed, I don't know if it's allowed to answer, you're going to get 2 answers. T is 2.31 seconds. I got that answer. I got another one too, actually. Negative 3.8. What's going on here? What's going on here is this negative 3.8836 seconds makes no sense. It doesn't work. It's inadmissible. I didn't throw that rock down and I went back in time. I mean, whatever. It's not a science fiction novel. Not allowed. Not allowed. But that is. And there's your answer. There's your answer. Let's keep going. So that was 50, let's see what that was, 57, yeah, right? That was 57. Let's look at 59. Now for 59, you guys, for 59, they're saying Tata launches a model rocket straight up from his backyard that takes 4.5 seconds to reach the maximum altitude. After launch, the rocket's motion is only influenced by gravity. A, what is the rocket's initial velocity? B, what is the maximum altitude reached by the rocket? Well, the maximum altitude reached by the rocket is when all of the initial velocity has been dissipated by acceleration due to gravity. Gravity is going to knock out, gravity is going to finish the initial velocity to the point, the initial velocity is going to be brought down to 0 at the very apex of the journey. VF will be 0 at the very top. How long does it take for that to happen when gravity's working on it? It's an interesting point. How high has it gone? So let's take a look at that. Let's see what we can say, guys. We got all the formulas that we need. Let's figure out where we're going. All right, so let's see what we have here, guys. Now, there's a lot of ways to play the game. If this thing's going up and this thing's going down, there's a lot that can get said. And I'll talk about it. When we get into two-dimensional motion, this is more or less one-dimensional motion. We do know something here. Didn't I tell you guys? If this thing's being fired straight up into you're not firing this thing downward where gravity's going to help you go faster and get the object to the ground faster. You're firing this object upward, and gravity is not going to allow this object to go too high. Gravity is going to be negative. Gravity is always negative. G is always negative. I told you, if everybody's going down and everybody's going one direction, downward, the negative distance and the negative acceleration and the negative speed, you could multiply all of that equation that you generate by -1 on each side, and it becomes positive. Basically, if everybody's going downward, you can treat everybody as positive. If it's going up and then down, you want to keep in mind the acceleration due to gravity is a deceleration. When it's going downward, it's as though the acceleration due to gravity is helping this thing go faster, even though it's going downward, even though technically it's a negative acceleration. If everything's going downward, if everything's negative, you can multiply both sides of any equation pertaining to that kind of stuff by a -1, and you got everything positive. When it's going up, then down, you got to be really careful. In general, again, it's in our mind, G is negative. G is negative. Well, they're asking for time. If they're asking for time, there's probably a number of things I got to remember, but here's one thing I got to remember. Down the road, VF equals VI plus AT. True. D equals VIT plus 1/2 AT squared. Yeah, I think I need that one. I think I need that one more than I need the other one. I mean, the other one is this, but the other one doesn't have time in it. The other one does not have time in it. So it might be an issue. D is this. You can do a whole bunch of stuff here to figure out what's going on here. Now, they're saying to us, they told us it was 4.5 seconds to do that. So I would probably, they're asking for the height and all this other stuff. You could play this a bunch of ways. I can use either one of these. The first thing to use, though, is that one. What's going on? For 59, if you take that, at the very top, the velocity is 0. Initially, I do not know how fast it was going, but I do know gravity was fighting it the whole time. A is equal to G. Multiply and get it over to the other side. Or just get it over to the other side. Add the opposite of it on each side. The initial throw, initial launch speed, VI equals 44.1 meters per second. This is the one to use. It's the one's going to get us there. So, hey, look, man, it lost all its velocity. Good. Well, how much velocity did it have to begin with then? If it lost all its velocity, it got down to 0. It must have started at something, and it was having its velocity dissipated at this rate, at negative 9.8 meters per second for 4.5 seconds. So how much velocity was lost? All of this. This is all the dissipation that occurred for there to be 0 velocity. How much dissipation is that? It's negative 44.1 meters of velocity was lost. What was the initial velocity? Positive 44.1 meters. So that's A. How high did it go? Yeah, I mean, I'm going to have to tell you. I mean, how high did it go? How high it went was, again, this we said the VI was, right? How high did it go, you guys, would have been, you can use either one of these. You can use this guy or this guy. It's all good. 44.1 times 4.5 seconds times 1/2 of negative 9.8 times the quantity 4.5 squared. You got to have negative. Here you got to have negative 2 also. In fact, let's use that one. Now you got to watch it. VF what is VF at the very top? It's 0. VF squared is 0 squared. What's the initial? Got to have negative 9.8 there. Why? Because that's going to be a negative. It's going to be a negative, whatever this is. 2 times this is negative 19.6. Negative divided by negative is positive. $99.225 meters. All right, that's 59. All right, I ended up, that's okay, or is it 59? Is it? Yeah, it is, okay. All right, guys, I did 57. I did 59. I did not, well, okay, let me get into the camera again. I did not plan on doing 59, but there it is. I mean, use it. Why not? Why not? That's fine. There's problem 59. I thought I was going to do I was going to move on and do some other problems with it, but I'll go on beyond that. So it's okay. Did not plan on doing that, but it's there and it's a great problem. That was 59. Let's do the following 2 problems, and then that'll end my discussion for chapters 1 and 2. Okay. Let's do problems 69 and 79. We'll take it from there. All right, guys, there's a number of ways we can do these. All right, problem 69. A trooper is moving due south along the freeway at a speed of 21 meters per second. At time t equals 0, red car passes the trooper. The red car moves with constant velocity of 28 meters per second southward also. At the instant the trooper's car is passed, the trooper begins to speed up at a constant rate of 2 meters per second. What is the maximum distance ahead of the trooper that is reached by the red car? Okay, that's a great question. What's going on here? What's the maximum distance this guy's going to go get away from the trooper? Well, there's a lot going on. He passes the trooper at t equals 0. At t equals 0, he passes the trooper. At that moment, he's as close to the trooper as he's going to get until the trooper catches up to him again. But there's going to be a maximum distance. He's only going 28 meters per second. He's not accelerating. The trooper's going 21 meters per second, but he is accelerating, so he's going to catch him. At that instant, the trooper speeds up. From 21 meters per second, he's going to start speeding up at 2 meters per second. The other guy just passed, and that was it. He's keeping a constant speed. What is going on here? At this, this already happened, and then there's a time where it's going to happen. I remember talking about this, man. There's a number of ways you can look at it. Make sure you're looking at my notes, guys. It's probably going to make more sense than make a lot of. Hopefully, it makes a lot of sense. There's a number of ways it can go. Let's just go for it. Let's just do it. Let me check on something real quick, if you don't mind. Okay. Let me see what I can say here, guys. Basically, at time, at time t equals 0, the guy's at the distance function d. How far has he gone? At time t equals 0, relative to each other, how far have they gone? How far is it going to go? There's a number of things to say here. I'm saying at time t equals 0, these guys are the same distance apart. At t equals 0, they've gone nowhere. We're going to start measuring distance at time t equals 0. At that time, they've gone nowhere. They're at a dead heat with each other. At another time, they're going to be even with each other because the police officer is going to catch them. So let's see how that plays out. D equals, so that's how the guy in the red car is going. And then police is going to be here. And his distance traveled is VIT plus 1/2 AT squared. VIT plus 1/2 AT squared. Police car? So we got this. D equals 28t. D equals 21t plus 1/2 times 2t squared. Let's talk. Let's set distance traveled equal. That happens at time t. That happens right when the guy passes him, and it happens when he gets caught. So that guy right there, that's the police car. And this is the guy who's passing the police car. Okay, let me subtract 28t on each side. Subtract 28t on each side. Gets down to something pretty easy. Factor a t out of there. Factor a t out of there. Degree 2 polynomial, two solutions. T equals 0 seconds, that's right when he passed, man. They both went the same distance. What distance did they go at time t equals 0? They went 0 distance. We're going to say that was distance 0. In 7 seconds, the guy caught him. T equals 0 seconds. T equals 0 seconds. This already happened. T equals 7 seconds. We got that. There's a number of ways to go here. So you put 7 seconds at either one of those, and this is when they meet again. So this is when they first met at T equals, and then 7 right here. So put 7 either in here or in here. It's going to be the same answer. 7 in here, that's 49, that's 1. 7 here, that's 147. 147, that's, right, because 7 times 21 is 147, and 49 is 196. If you put 7 right here, it's going to be 196 also. So the two distances, they meet at d equals 0 and they meet at d equals 196. Well, it's pretty fascinating in its own right. What happened here, guys, is we set it equal to 0. What you could have done, a number of ways to go here, actually. What you could have done on this, I think one of my students pointed this out some time ago. This is fine. What's been happening here? And I know you set it equal to 0. Do you guys mind if I call capital D? Let me try to write it nicely. Let me call capital D D of the red car minus D of the police car. I want that to be a maximum. I did it a little differently when I did it here. There's a number of ways to do it, but this is the kind of the way I did it afterwards. What is that? What's the red car? 28. What's the police car? Red car is 28T. Red car is 28T. Police car is 21T plus a half times 2T squared. That's 1T squared. 28T plus 1T squared. when you do it, you got 7t minus t squared. Okay, yeah, when's that going to be at a maximum? It's going to be at a maximum, max min. Here there's a max, there's a min. Take the first derivative, set it equal to 0. Zero equals 7 minus 2t. Ladies and gentlemen, at 3.5 seconds, the max is going to occur. The maximum distance apart is going to occur there. If that's the case, put 3.5 right here. Put 3.5 right here. 3.5 times 7, and here put 3.5 times 3.5. Pretty fascinating stuff. So what's going on here? What's going on is it's going to be 12 point, you actually plug it in there. Put 3.5 right here times 7 is going to be 24.5. Put 3.5 right here and square it, it's going to be 12.25. 24.5 minus 12.25 is going to be 12.25. The maximum D that's going to occur, D max equals the D here is going to be 12.25. 12.25 meters. There's other ways to go about it. I think the way I did it, no, I did it. That's essentially the way it goes. That's essentially, and you'll see that in my notes as well. That's essentially the way it's going. So that's problem number 69. Problem 79. Problem 79, a hydrogen atom moves along the z-axis of a bubble chamber according to the equation z equals 5.00 t squared plus 4.00 t, where z is in meters and t is in seconds. What is the average velocity during the time interval A, t equals 2.5 to 3.5 seconds? So from 2.5 seconds to 3.5 seconds, what's the average velocity? B, what's the average velocity from 3.5 to 3.6 seconds? So let's see how that one plays out. Fascinating how this problem went about, guys. I mean, that's the big thing. We've got a formula for how the red car is moving at a constant speed. He's going pretty fast, and he's not accelerating in any way, not slowing down, not speeding up. The police officer does speed up, though he was going slow initially. At t equals 0, they are in a dead heat with one another. At t equals 7 seconds, they're back to a dead heat with one another. Somewhere between 0 seconds and 7 seconds, somewhere between, at 0 seconds, they're in a dead heat with one another. There's no distance between them. And at 7 seconds, we found out there's no distance between them. The red car gets caught by the police car at that point. 0 seconds, no distance between them. 7 seconds, no distance between them. Between 0 and 7 seconds, somewhere there's a maximum distance between them. You could take this function right here, we actually, in a backhanded way, we actually ended up solving it that way. In a backhanded way, set it equal to 0. 0 is the distance, but that could also be the d function. When you could, depending which one you want to call the distance between them. That's not the real big deal here. It'd be a negative number or a positive number, not a big deal. Because the red car's ahead, you write it like this. If you set it equal to 0, guys, you can just have the 7t in front and the t squared in the back of that. It means the same thing. You set it equal to 0, you get this. No big deal. This is the d function. If you find the two zeros of the d function, there is, it's looking something like this. Actually, this is significant, actually. 7t minus t squared if this is 0 and that's 7, and every parabola of this nature has symmetry, where's the highest part going to be, guys? If this is 0 and that's 7, this is 3.5. Plug 3.5 into here. Plug 3.5 into here, and you end up getting the 12.25 that we were talking about. So that's another way to look at it. Kind of neat. All right. This will be the last problem in this section, you guys. So let's talk about it. Let's see how that all plays out with the hydrogen ion, and we'll take it from there. All right, let's see how this plays out. They're saying in the z direction, so we're going to figure out exactly how we're going to say this. You got to find averages, is what you got to find. And that's okay. So we're not doing a calculus problem on this one, but on problem 6, what was that just now? I think it was, forgive me here, let me just see that, guys. Right, with the trooper. For problem number 69, you sort of got compelled to make it into a calculus problem. Now notice when I drew that parabola, because of the symmetry of the parabola between 0 and 7 is 3.5. 3.5 is where the max is going to occur. So I got out of using calculus if I wanted to. So 79, z equals 5t squared plus 4t. Z equals 5t squared plus 4t. I don't know. There's a lot of ways we could play it. They're talking about everything in the z direction. They're not talking about this thing going any other direction. So, this might be. Let's see how it plays out. Let's see how we want to play this thing, guys. The average. The vector location, it is in the z direction, so I got to talk about direction, I got to talk about location. That's got vector written all over it. If that's the case, the average v vector is, what are they trying to say here? The average v vector is, and there's a lot of ways to do this. Let me see exactly what the heck I'm going to do here. Right, there's a number of ways this can be written. For some reason, I wrote this in a way that I myself am not even thrilled about, but this is what's getting used. Put a T2 right here, put a T2 right there. Good. Put a T1 right here, put a T1 right there for the other one. You can, I don't know, whatever. This is kind of a horse piece, guys. I mean, how you want to do this. Yeah, there's so many ways to write this. Take this thing right here, and pull the T out of there, and say, hey, man, look, T2. Here's T2, here's T2. Let me pull it out of there and let's leave that T right there. I don't know, maybe this made it easier to look at. I'm kind of questioning what the heck I was thinking when I wrote it like that, but let me keep it consistent. You don't have to do what I'm doing here. The T1 is 5T1 plus 4. And that's just, this bookkeeping here is in the K direction. Subtract time T2, the stopwatch, time T1, the other stopwatch. I mean, when you start out. You didn't have to keep it like it. You could have kept this. You could have made this. Bring this guy in here. It's 5T2 squared plus 4T2. This is 5T1 squared plus 4T1. All right, so you guys, it doesn't matter. That's not the big deal. You plug in. For A, they said you started at 2.5 seconds and you ended at 3.5 seconds. 2.5 seconds, you started at 2.5 seconds, the clock started at 2.5 seconds, and it ends at 3.5 seconds. 3.5 minus 2.5. 3.5, 3.5, 2.5, 2.5. Put it in there, guys. Grind the numbers out. So let's see what we got. So when you actually do it, you grind the whole thing. Let me see. What do we got here? All right, we got 34. You got that. They put like this. Sometimes they put the K out in front. Again, guys, just make sure this is, I don't know, you can argue this one all day long. This is probably the better way to write it. Put the vector quantity, then have the scalar right at the end. I don't know that it makes a hill of beans a difference, but just watch it. Make sure we're giving the answers as we should. Proceed in the same manner, guys, with the other one. The other one's 3.5, 3.6. The other one is saying, for something like this, start at 3.5, go to 3.6. This is 3.6, that's 3.6. This is 3.5, that's 3.5. This is 3.6, that's 3.6, 3.5, that's 0.1 on the bottom. It's the same kind of thing. Plug in the numbers, you guys. Plug in the numbers. It was a lot different with the other one. The other one was 2.5 to 3.5, that's 1 second. 3.5, 3.5, 2.5, 2.5, grind it all out. This is 3.5, this is 2.5, that's 1 whole second. The other one, B, is 3.5 and 3.6. It's not 1 second difference, it's 0.1 second difference. 3.5, 3.6, 0.1 second. Just 0.1 second of a difference here. 3.6, 3.5, 3.6, 3.6, 3.5, 3.5. So that's, this one was A. The other one, you grind it out, you plug them in there for B. And that's going to come out to 39.5 K vector meters per second. Bigger answer, but the time frame was smaller. That's all right. The bottom number is small, so when you divide by a small number, you get a big answer. Well, you're not going to get as big an answer here because the difference between them was pretty small. So this probably ain't a big difference, but that's okay. This ain't a big difference either. So the ratio should be right about in the ballpark. Again, that's in my notes when we actually do it. But the big takeaway here, I'm kind of baffled why I wrote it like this. I could have just easily written it for both situations, you guys. Both situations. Here's 5t2 squared minus 4t2. Maybe it's a little easier to look at. I don't know. Perhaps it was easier to look at. I don't know. You got this minus so 5t2 squared plus 4t2. Is that a 4? I'm sorry. Yeah. Plus 5t2 squared plus 4t2 minus 5t1 squared plus 4t1. Probably a more logical way to write it. As most people in my family will tell you, I'm not really associated with logic all the time, but all right, well, there it is. I mean, so you're looking at something like that. It's probably an easier, a little more straightforward way to write it. It's a horse apiece, guys. These are the same thing. These are the same thing. It's the same thing. Just for each scenario, for the first scenario, you're putting in for part A 2.5 and 3.5. So 3.5 right here, square it, multiply. Maybe it's just a little easier to do it like this. Either way, it's a horse apiece, guys. It works either way. The quantity 3.5 squared, the quantity 3.5 squared times 5 plus 4 times the quantity 3.5. The quantity 2.5 squared times 5 plus 4 times the quantity 2.5. So all of this, the quantity 3.5 put into here, quantity 3.5 squared times 5 plus 4 times the quantity 3.5. Get an answer. Then get an answer here with 5 times the square of 2.5 plus 4 times 2.5. Get an answer here. This answer minus that answer, get an answer, then go 3.5 minus 2.5, which is 1. You'll get the answer. You'll get the answer that I've already erased at this point, guys. I think this was B. We actually did it. Yeah, this was A, rather. This was A, so that's A. And then you just do the same thing. But instead of what we had for A was 2.5 and 3.5. So 3.5 right here, 2.5 right there. This other one is 3.5 and 3.6. 3.6, 3.5. 3.6 in there, 3.5 right there. And that's going to bring you to here. So this is A, and this is B. And that's A. All right, guys, that's chapters 1 and 2, and a little bit of discussion pertaining to some of it. And, okay, that's it. That's chapters 1 and 2. We'll keep going. We'll do the best we can with this thing, and that's about it. Take care, you guys. Appreciate your time. Cut.